let's do this. Question 1. So this question want us to determine whether A is diagonalizable or not. Okay. If it is, find the matrix P that diagonalizes A and determine P inverse AP. Okay. So for this question, these are the steps. Okay. So the first step, you need to find the eigenvalues of A, and A is n by n matrix. Okay. Then you find the eigenvectors corresponds to the eigenvalues. After that, you check whether the set of eigenvectors form a basis of Rn or not. Or you can also check whether there is n linearly independent vectors in the set or not. Okay. If yes, then we can write our P as a matrix of eigenvectors, where you write these eigenvectors in column form and you list it this way. If not, then there is no P, means A is not diagonalizable. Suppose we have P, then P inverse AP will be a diagonal matrix which entries for the main diagonal are the eigenvalues. Let's just do this question, part A. So this is my matrix A. So A is, for this question, A is 2, 0, minus 2, 0, 3, 0, 0, 0, 3. Okay. We want to find eigenvalues, and the eigenvectors corresponds to the eigenvalues. So basically, what is eigenvalues and eigenvectors? So if we consider the equation Ax equals to lambda x, where x is not zero vector, the x here is eigenvector, the lambda here is eigenvalue, correspond to that eigenvector. Okay, so to find eigenvalue, okay, we consider this equation. 0 equals to the determinant of lambda I minus A, and this is just the determinant of lambda minus 2, 0, 2, 0, lambda minus 3, 0, 0, 0, lambda minus 3. And we see that this is actually a triangular matrix. So the determinant of this is just the multiple of the diagonal entries. So I have lambda minus 2 times lambda minus 3 take square. So we have lambda is equal to 2 or lambda is equal to 3. And these are my eigenvalues. Okay. Next step, I need to find eigenvectors corresponds to these eigenvalues. So first, for lambda equals to 2, we have we want to find x that is not 0, such that ax equals to lambda x. Here lambda is 2, so 2x. Okay. Or we can also say that 2I minus ax is equal to 0. Okay. So this thing, okay, this thing, I want to write it in terms of matrix form. Okay, so we have (2i minus a) is actually this matrix with lambda is equal to 2. So we have 0, 0, 2, 0, minus 1, 0, 0, 0, minus 1. Multiply with x1, x2, x3 is equal to 0, 0, 0. Okay. You can make this into augmented form and make it into the raw echelon form. But then I think this is simple enough for us to do it manually. And it might be faster. You see here, the first element of this will be 2x3. Second element will be minus x2. The third element will be minus x3. 0, 0, 0. Okay, and this means, if we see this, this means x2 is equal to 0. Okay, this means x3 is equal to 0, and it is consistent with this. So we have x2 must be 0, x3 must be 0, but x1 can be anything. So I just make it as a free variable. Okay, so hence we have found our x. X is just x1, x2, x3, which is t00. 0. I can write this as t100, and I can pick this as my eigenvector. Corresponds to this eigenvalue. Okay, good. Next, right here, for lambda is equal to 3, if I'm not wrong. Yes, same thing. We want to find x that is not 0, such that 3i minus a x is equal to 0. So we have 3i minus a will be 1, 0, 2, 0, 0, 0, 0, 0, 0, x1, x2, x3, 0, 0, 0. This means I have x1 plus 2x3 is equal to 0, and we don't care what is my x2. Right? I can make it as free parameter. And if we see this thing, okay, this means no matter what is my x3, I can find x1. So I can make x3 as another free parameter. Okay. Hence, my x is just x1, which is minus 2 times x3, which is minus 2s. And x2 is t, x3 is s. So I get I take out my s minus 2 0 1 plus t times 0 1 0, okay, where s and t is just real numbers. Okay, and we can pick these two as my eigenvectors. Okay, very good. So we are done with step 2. Now we go to step 3. Okay, we want to check whether if I take the union of these two, okay, this vector, this vector, this vector, it will be linearly independent or not. Okay, to do that, there's a trick. What you need to see is just whether this is linearly independent or not, and whether these two, the set containing these two vectors, is linearly independent or not. Okay, if this is linear, the set containing this vector is linearly independent, and the set containing these two vectors is linearly independent, then we can conclude that the union of these three vectors, they are linearly independent. Okay, so clearly this is linearly independent. Okay, since set is okay, and this set, okay, containing these two vectors is also linearly independent. Sorry. The set, okay, of the union of these two is linearly independent. Okay, and okay, I forgot to mention there are three. Okay, there are three of them. So there are this matrix is 3 by 3 matrix, and there is 3 linearly independent vectors. Okay, so I can write my P. Okay, I can write my P. Therefore, okay, I can write my P, and my P, we just need to make this in terms of column vector and list it. So I have 1 0 0 minus 2 0 1 and 0 1 0. Okay, good. And by using this P, okay, by using this P, P inverse P, P will be a diagonal matrix, and the diagonal entries, let's say for this one, okay, it is the eigenvalue of this eigenvector. So it is 2 here. Okay, for this it is the eigenvalue of this vector. So it is 3 here, and same thing here will be 3. Okay, you can check this. Okay. So in conclusion, A is diagonalizable. Okay. Okay. Hope it is clear. I will not do part B. I think they are the same. I will do C in the next video.